Huh? Where am I?
So, you finally came.
Angie's? What are you doing here? Can you tell me where I am?
Of course! Welcome, Sayo, to the math room. For the next 3 months, you'll be here solving one math problem per week. Do you think you'll be okay with that?
Huh? Sure, I guess.
Good! I'm Angie's, and welcome to Summer of Maths Exposition, or... So, last year, I brought up this problem. Starting with a square piece of paper, is it possible to cut it into pieces and rearrange them into any possible straight edge shape with the same area?
What? That's it? That sounds so easy.
If it's so easy, then what's the answer? You see, it is possible.
For every shape? How would you even go about proving that?
You see, this question is equivalent to this other question. Can you turn any shape into any other shape by cutting it and recombining it?
That's right, because if you can turn a square into a shape, then you can turn that shape into a square, and then turn that square into a different shape.
That's correct! First of all, you can see that we can cut any shape into triangles, right?
Yeah. Wait, then we can turn the triangles into parallelograms by cutting it in half and moving this top piece, and then we can turn these parallelograms into rectangles. And after that, we can turn these rectangles into a square. How do we join these rectangles together? For some set of rectangles, like those with all rational sides, it works. But these rectangles can have any side lengths. There's no way to prove we can mesh together these rectangles.
Don't worry, I can show you a trick. First, you need to align the starting rectangle and the target rectangle to the bottom left-hand corner. You may need to chop it up into equal parts and rearrange it so that the left side of the starting rectangle is between half and twice the left side of the target. Then, draw a line from the top left corner to the bottom right corner. Then slide the resulting triangle so that it's in the target. After that, you can cut off the excess and fill in the gap like so.
I see. Mind explaining how that works?
Of course! Let's label the sides of the shorter and thicker triangle A and B, and the sides of the longer and thinner triangle C and D. Either rectangle can be the target or the starting in this case. It doesn't really matter for the proof. What we want to show is this shape is the exact same as this shape, and this shape is the same as this shape. We can see that this side is A minus C. Notice how this triangle is similar to this triangle since they're both right angles and they share a corner. Therefore, D over A is the same as this long side over A minus C. Rearranging, we get that the length of this side is D minus DC over A. But DC is the area of one of the rectangles, which is the area of the other rectangle, AB. So we get that the length of the side is D minus B, which is exactly the same as this side.
I understand. Wait, but these two triangles are also similar.
That's correct, and since they're similar, these two angles must be the same. And via the angle side angle theorem, we get that these two triangles are congruent.
So, what next?
Well, since these two triangles are congruent, these two sides must be the same, A minus C. This means the length of this side is C, the same as this side. And since these two angles are corresponding, then they must be the same. Again, with the ASA theorem, these two triangles are congruent.
I get it now. So now that we can change rectangles into any other rectangle with the same area, we just need to turn these rectangles into ones that have the side lengths of the square.
That's correct. And after we stuck all these rectangles together, we can redivide them, turn them back into triangles, and form our new shape. We've proven it.
That's so cool.
This is called the One-Scoliosis theorem.
Say, is there an equivalent for 3 dimensions?
There is, but unfortunately, in 3 dimensions, you can't turn any shape into any other shape. There's this something called the Dane invariant that doesn't change no matter how much cutting and gluing you do to a shape. You can learn about it more in this video, where I got this theorem a long time ago. Well, I think that does it for now. Take care and see you next